Okay, so we have more back-to-back panels, but don't worry, there's trivia and cool lights again, so we'll make it exciting. And we're starting off this afternoon with our Ready to Go panel, and I'm going to let Mark take it away from there.
Okay, well, good afternoon, everybody. Hope you had a good lunch. We have an exciting panel for you so that you don't fall asleep in your chair while we get going. So if you were here yesterday and were a part of, listen to Nikki Werkheiser's panel, we heard about all of the, a bunch of the payloads that had recently gone to the moon and heard about their experiences and their successes. In this panel, we're going to actually look forward and we're going to hear about a new round of commercial technologies, a new wave of STMD partnerships that are on the edge of being realized and will be here, and they will be on their way to the moon shortly, right? We're going to hear from each of them for a few minutes about their individual technologies and what is in store for them as they work to bolster an emerging lunar ecosystem. So very quickly, we have Dr. Andrew Lange from Blue Origin to talk about Blue Alchemist. We have Brant White from Sierra Space to talk about Carbothermal Oxygen Production Reactor. Evan Jensen from ICON to discuss MMPACT, which is Moon to Mars Planetary Autonomous Construction Technologies. I wrote it down. And Steve Clarke from Astrobotic to discuss lunar surface power infrastructure. And just as a reminder, if while you're listening, you have a question that you want to ask, please log on to the Slido site, post your question. If you see a question that is interesting to you, make sure you upvote it. And when we're done with these presentations, we'll go to the questions and spend some time discussing those. So I'm going to hand it over to Andrew Lange and get us started.
Great. Thanks, Mark, and thanks to all the organizers at LSIC. This is an incredible event, and for those of us on the Space Resources team, the LSIC working groups and these conferences are really instrumental in getting us up to speed on what's going on in the community. So today I'm going to be giving an update on behalf of the Space Resources program on our Blue Alchemist technology. So this is a project that's a STMD tipping point partnership with NASA. So first, kind of a quick shout out for the support from Nikki Werkheiser, as well as our PIM, Quinyao Nugent, and our technical POC, Janine Captain. This partnership has been very, very instrumental in helping us accelerate the technologies that we're developing in the lab today toward flight as quickly as possible. So we're looking forward to delivering these in a vacuum chamber soon and then pushing them toward flight as quickly as possible. So as you heard from John Caloris yesterday, Blue Origin has a number of drivers. The first is building a road to space, and we accomplished that through our New Glenn rocket as well as our New Shepard rocket, as well as the landers that are being developed within the Lunar Permanence team. The second gate or the second driver is inspiring the next generation. So we largely do that through our Club for the Future organization. And the third gate is harnessing the resources of space. So that's where our team comes in. And right now we're heavily focused on building technologies and products for the lunar surface with extensibility to other planetary bodies. So obviously Mars falls in there, but also leveraging those technologies for the benefit of Earth as well. So this on the right is an early prototype solar cell that was fabricated by our team back when we were at Honeybee Robotics. So our team currently inhabits the Space Resources Center of Excellence at Blue. We're in Los Angeles, California, specifically in North Hollywood. We've grown very rapidly over the last few years. We've grown from about 20 people to about 60 staff currently. And we've also grown in space. Just about a year and a half ago, we were at Honeybee Robotics, so shout out to our colleagues in the audience for giving us a place to live for a period of time. But the little yellow square in the bottom left corner shows our footprint at Honeybee Robotics about a year and a half ago relative to the size of our facility today. And in these images, you can see we have a number of very large vacuum chambers for testing our systems, our end-to-end systems in a lunar relevant environment. We have a lot of capabilities for testing thermal processing systems such as our MRE system, our silicon purification system in relevant environments. We also have a vertically integrated machine shop which allows us to fabricate immediately from design all the way to prototype. We have an on-site analytics lab, which allows us to characterize all the things going into our system, as well as the products coming out. And we also have a regolith simulant lab, which allows us to make custom simulants in-house. So maybe before going to this slide, also a shout out, we do have a couple of open recs. So if people are interested in joining our team in sunny Southern California, please visit careers@blueorigin.com. So today I'm talking about the Blue Alchemist system. This is an artist rendering of the initial architecture of the Blue Alchemist system. It's a mobile unit that crawls across the lunar surface, ingests regolith, processes the regolith to extract metals and oxygen, and then processes the silicon and those metals to produce solar panels, and then autonomously connects those panels together to provide power on the surface of the moon. So the primary product of this system is obviously solar power. So power is very much needed on the lunar surface to enable a lunar economy. But we are also thinking about other products that are coming out of the system, specifically oxygen and some of the refined materials that come out of our MRE system. So going to that first product line, solar power, on the top left here, you see some solar cells that we fabricated in our laboratory. You can see those on our table out in the lobby. It's a very simple process. It requires about 3 or 4 steps. We've achieved our target efficiency of 7% solar cell efficiency. We are developing a protective cover glass which will extend the lifetime of the solar cells. And the cover glass is currently undergoing radiation testing. The process is fully automated, and we're currently testing that automation process in one of our large vacuum chambers. So obviously, to make high-efficiency solar cells, we need very pure silicon. So we've developed a process to purify the silicon by growing large boules of silicon, a single crystal silicon. That process requires no reagents, and we're capable of removing impurities down to 99.9999% silicon. And this platform, which will be tested again in a large vacuum chamber, will be a first of its kind capability for crystal growth in cislunar space. So oxygen is sort of the next product line that we're developing through our MRE process. We've been able to develop a oxygen-compatible MRE cell. So on the top right here, you see some bubbles coming out of the melt during the MRE process. We've been able to achieve capture efficiencies up to about 98% oxygen capture, and what that means is of the oxygen that's produced or generated in the melt, we're detecting 98% of that downstream. We've seen consistent production rates up to about 0.26 grams of oxygen per amp hour, which enables us to scale this to metric tons of oxygen production on the lunar surface per year. And so as you've heard from our Blue Origin colleagues earlier, Hydrolox is sort of the baseline architecture for Blue Origin. And so this is a critical capability which will allow extensibility for future missions in space. And this oxygen will also enable other near-term Artemis objectives, such as providing contingencies for breathable oxygen as well. We've been able to achieve our goal of 11% oxygen extraction by weight of regolith, and in this case, LHT1, at the kilogram scale. And we've also extensively characterized the impurity volatiles that are coming out of the regolith, both during melting and during MRE. That has been largely enabled by a partnership that we have with KSC, which is established through this STMD Tipping Point Award, where we've been able to leverage flight-forward hardware so that once we have an integrated oxygen production system, we can push it to flight as quickly as possible. And along that same vein, we're currently testing an integrated system for oxygen production to purification and storage, leveraging a partnership with Johnson Space Center using their MCOG system, which allows us to purify the oxygen and compress it. Furthermore, we can leverage previous NASA investments, such as an STMD Tipping Point Award for liquefaction, zero boil-off, which has been discussed a few times during this meeting, in order to store the oxygen long-term for these propellant applications. So finally, some of the refined materials that are coming out of our system, we're able to extract iron, silicon, and aluminum, as well as some of the intermediate metals during the electrolysis process. We also are able to generate glasses and ceramic materials from the leftover slag during this electrolysis process. We've been able to extract our target of 100% of the iron from Highlands composition regolith, as well as 10% of the silicon by weight of LHT1. And we've been able to determine what the current efficiency is, or the oxygen extraction efficiency, dynamically through this process. So looking forward to oxygen production systems or metal production systems, we understand the power requirements of these systems dynamically. And our aluminum reactor and cell are currently under development to be delivered sometime this summer. So some other accomplishments related to downstream material refining. We've been working extensively on developing systems to melt regolith efficiently, and we've been able to reduce the amount of energy required to melt regolith by about an order of magnitude from our baseline, as well as melt regolith in as little as about 2.5 hours at relevant batch scales. Again, we've been able to characterize the volatiles that are desorbed during melting, and so we have a very good understanding of how we would separate volatiles from impurities that might influence downstream sub-processes. And last year, we delivered our aluminum wire production system, and you see an image of that on the top right here, which allows us to produce wire from aluminum extracted during our MRE process. And finally, we are thinking about our system as a modular system. So the capabilities that we're developing to make materials such as aluminum wire, we're trying to make them extensible for regolith and other metals so that we can cast and produce metals for ISRU structures and other capabilities that are needed for near-term Artemis missions. Thank you.
Great, thank you very much. This is a great example of where through a tipping point award that industry and NASA are able to work together and provide you expertise and facilities and such that you need. It's a great example of that.
Yeah, absolutely. I'll double down on the influence of the partnership in connecting us with the centers, and the technical capabilities across NASA have been really, really significant in helping us accelerate both the technology development, but also thinking about how we integrate these technologies to make an impact in the near term on the lunar surface.
Yeah, absolutely. Okay, Brant, take us away.
All right, so again, I'm Brant White from Sierra Space. I've been working on Carbothermal for, I'm dating myself, but over 20 years now. I started fresh out of college there as the lead engineer on Carbothermal, and then I left for a couple years. When I came back in 2020 or so, took over as more on the program management end. So I do miss the engineering, but at least I get to be in the lab some. They don't let me run the hardware, unfortunately, anymore. Our Carbothermal technology, though, it really dates itself back to about 1995 is when, as a company, we started working on it. And it's really a SBIR success story. Back then, we were a small company, eventually got acquired by SMC and Sierra Space. But there's a lot of SBIR projects that we worked for a decade or so, really working through the nitty-gritty of how to get this to work and coming up with the novel concepts and everything. And then that parlayed itself into a tipping point that we won and had executed here. So that's what I'll cover today. So just as a kind of background, I'm sure several of you have heard this. I get sick of talking about this because I do it every time. But the carbothermal reduction process, just to give you a good overview of it, carbothermal reduction itself is a mature terrestrial technology. They use it to make silica from sand, essentially. But we pair that with two other steps then to get oxygen extraction. So the focus of what we do is that first step and actually extracting the oxygen from the minerals and the regolith. But downstream of that then, that material comes off, the oxygen comes off as CO and CO2. You run that through like a Sabatier reactor or catalyst bed that with some hydrogen gas, that converts it to methane. You can use methane basically as, you're using a carbon reactant of some sort, because ultimately the methane cracks on your hot melt surface, the carbon diffuses in, extracts that oxygen out there. So you have to regenerate that methane, you make water in that catalyst process, then you send the water to an electrolysis bed to electrolyze it. So at the end of the day, it's regolith in, energy in, oxygen out and like melted regolith out that's solidified, but it's more like a rich ore. The metals aren't completely separated in there, but they're reduced. So you could do post-processing on that. That's outside the scope of what we've done to date. All right. So 2 major projects as of recent, at least, are what I'm going to cover. So CTOP was an SBIR phase 3 that we had with NASA. That was done in the early 2000s. That was, again, kind of the culmination of the prior SBIRs and technology development we had done. But CTOP was a lab scale, non-flight-like demonstrator that really showed all of the technologies you need to do and processing steps you need to do to extract that oxygen from the regolith. So we're going all the way from bringing regolith in, picture a arm or excavator dumping the regolith into a hopper, and that's when we start taking it over. So you bring that regolith into a pressure boundary, you get it into your processing chamber, you do whatever preparatory steps you have to do to get it ready to get melted. Then you do that melting, to extract the oxygen, you let those melts solidify, and then you pick those melts out of the regolith and get them out of your system again. So I didn't mention it was on the prior slide, I think. One of the big novel things we had come up with is, that molten regolith material is hotter than lava, and I'm sure all of you know, if you put lava in a cup, the cup's not going to last very long. There's lots of materials challenges there. So what we did in one of our novel concepts here is by using direct solar concentrated energy, we can beam that in. In the lab, we use a laser to simulate that. But you just melt a bed of regolith, and just the center portion where you're applying that energy to becomes melted. It's surrounded by other regolith, so you don't have to worry about a container degrading or anything like that. So on CTOP, that's what we're doing. On CTOP, we were making multiple melts at the same time. The actual size of an individual melt was the size you would need to do the 10 metric ton per year oxygen production rate. That's kind of the nominal, baseline case here. So that way, all we do for scalability is add more melts to the system. CTOP wasn't making 10 metric tons per year, but it was demonstrating that core unit that then gets scaled forward. So CTOP, worked well, but again, nothing about that was flight-like. So after finishing that project, we had won the COPR Tipping Point Award. So that was a really great partnership with NASA. We had put IRAD in on CTOP, but we also obviously had a cost share contribution on COPR. And then that let us really look at CTOP and think, okay, what can we do to miniaturize this, to put it on a CLIPS-sized lander, but still demonstrate all the core technologies and functionalities you need that would be applicable to that, pilot plant or precursor pilot plant for oxygen production. So that was really about miniaturizing it. CTOP did a steady state, type of process. COPR instead think of it more batch-wise. So I talked about getting regolith in and then prepping it for the reaction, doing the reaction, getting the melt out. That was all continuous in CTOP, happening in different areas. COPR, you kind of have it batch-wise, and you're just going sequentially through those steps. But that allows us to show all those key technologies on a much smaller, mass scale that you can throw on, several of the CLIPS landers that have already been talked about over the course of this meeting. So the real goal then with COPR, after we TVAC test that, get that up to TRL 6, and then that would be really the blueprint essentially for a Lift 1 mission or something like that to do the actual demo on the lunar surface. So there you can see again the COPR unit. It's the big box down below it and everything is just kind of support hardware, but that's the COPR unit in the TVAC chamber, the dirty TVAC chamber at JSC. So we did testing with that back in the end of July, early August of last year. I'll get to some of the conclusions with that here as well. But it's at an angle on there, because the lunar topography, they think slope angles might be up to 10 degrees. We're flowing regolith through that system, so we're very concerned, as Icon had showed, about how regolith can bridge and things like that. So we've been able to demo all that, but we want to make sure if you land on a slope, we're not just thinking of this on level ground. So that's oriented in like the worst case position for our systems where slope would most negatively affect it. It also just so happens that the laser energy coming into the melt, that's at 15 degrees. It happens that the window overhead in the chamber where the laser comes in is at a 15-degree location, and that chamber existed since the Apollo days, so we weren't changing that. So here you can see the pyrometer there is not aligned directly to it, but the melt is there in the upper right corner. It's the brightest patch you see there. So that's processing under TVAC conditions. You see it moving around and stuff. What happens is that melt forms, its surface tension causes it to drop into a ball, and then it kind of sinks down into the regolith some as you're processing it. It's moving around there because as you're creating CO gas and a little bit of CO2, depends on the regolith makeup, that's just causing it to move around, and it's energetic enough as it does that it can also fling a limited distance some of the regolith particles, so you see some pop there in front of the frame as that's happening. So that's the reaction actually happening in TVAC. But on top of that, again, we successfully demonstrated all the different steps in there. So the regolith handling operations, we have to, from that hopper, we have to meter the flow of regolith into it. We have to measure how much we put into the system and transport that through the system. We also have to seal that in a pressurized container, essentially, when we do the carbothermal reaction to get the CO2 gas out of it. So we do that reaction in there, and then once the melt solidifies, we demonstrate how we remove that melt from the system. So we did multiple tests with this at vacuum conditions and at the thermal vacuum conditions last year then to bring this up to TRL6. Just as a side note too, this was something that we demonstrated, I'm going ahead on my slides here actually, so I'll go one more. This was something we had demonstrated before in 2010 out in Mauna Kea on the International Lunar Surface Operations field test, was an end-to-end dust to thrust, production of oxygen, doing the whole electrolysis process and everything. The scope of COPR was just to make the CO in this case. So going forward, we're still partnered with NASA. NASA has the CARD program. So NASA has developed a solar concentrator. This one is different than the one we field tested in Hawaii back in 2010, because back then the plan was to go to equatorial regions. In the South Pole region, the sun's obviously just off the horizon, so you use a different type of mirror system. This is called a cross-dragon. So NASA developed all this. They reached out to an industry partner they have that has flight heritage on these carbon fiber mirrors. So that was great because we would have never known those existed. But between, I hope I'm not forgetting anybody, but between NASA JSC, KSC, and Glenn, they've developed avionics, that mirror deployment system, sun tracking system, all of that. So we'll pair that with our copper hardware here come this summer and test this using actual sunlight again. So that should bring kind of the whole package up to TRL6, so that the next logical step there would be to do a flight. And that's everything for me.
Great, thank you very much. All right. Okay, we're gonna move right into Evan for Impact.
Excellent. Yeah, I'm Evan Jensen from Icon Technology, but today presenting on behalf of the MMPACT project, which is an STMD project managed out of Marshall Space Flight Center. MMPACT is, as you said before, Moon to Mars planetary autonomous construction technology. Essentially the objective to develop on-demand capabilities to protect astronauts and create infrastructure on the lunar and Martian surfaces. Construction of landing pads, roads, shelters, and habitats using locally sourced ISRU materials. Had to read it to make sure I got it right. We have presented MMPACT over the years at LSIC actually, and I try to put out a little bit more information as we make progress, specifically on this panel because we're talking about ready to go. I thought about how to tell the story, and essentially I thought really just the TRL progression sort of makes the best story. And so these renders are getting a little bit tired, honestly, because we did them 4 or so years ago when we were just really thinking about this. This principle of TRL1, what if we had a moon base? Let's draw a picture of a moon base. What would it look like? What would the requirements be? How do we master planet? How do we think about asset adjacency and what are our needs there? Do we need to be by a permanently shadowed region? Does that put us at the South Pole? Do we need to be equatorial? I don't know. So we started thinking about this, and we put a good bit of thought in, but it was pretty early stage as well. So we worked with space architects and some other folks to really put some level of definition just to make sure that we didn't engineer the wrong solution to the problem. One more principle, what if someday there was a Mars base? So Moon to Mars, the Moon to Mars program at NASA, of course, spawned MMPACT, and so we certainly have all of these technologies in mind for Mars as well. So then we got on to TRL2, which is what I call application formulation of surface structure elements. So we started sort of breaking these elements that we wanted in the future in our TRL1 level into things like horizontal construction, vertical construction, because you may need different techniques for each one of them. We also thought as phased approaches, so what would be the first thing we needed and what would be most appropriate and when. First, we thought horizontal structures like landing pads, berms, roads, protective structures on into phase 2 and 3, master planning, strategic expansion and such. So we hope to get there at some point, but primarily, sorry for the alignment there, but infrastructure services is what we're after to provide support for all of these possible different futures that we haven't yet totally defined holistically into some sort of master plan that's time phased. But all of these things on the screen are things that we've looked at, we've thought about how we might do that. So we call that sort of architecting from the right, again, to make sure we don't build the wrong solution. And so TRL2, kind of check mark on that. We felt pretty good. It was time to move on to TRL3, which is what I call proving the concept, the materials, and processes. So we took a look at a bunch of different ISRU technologies, specifically did a pretty deep dive on the literature. A lot of these are not brand new ideas, but hadn't necessarily been matured up through the TRL scale, especially at the time that we were starting 3 or 4 years ago. So we went through molten extrusion for casting. As you might picture, the output of these Carbothermal and MRE systems already have a substantial amount of embodied energy. So that costs us money to embody, right? Or time, and time is money essentially on the surface. And so being able to cast and potentially controlled extrude molten material was of a lot of interest to us, as well as laser-directed energy deposition, that second row there, including things like microwave sintering that the MMPACT project has put a lot of energy into, as well as cementitious, so a lot more close to what ICON does terrestrially for our business, by using ISRU-based cementitious materials that are technically feasible on the Moon and Mars. So we sort of move this through a filter to the right of what we want to demonstrate, looking at high TRL viability and relevant environmental, and just making sure that CONOPS could actually close for these sorts of things. So today I'm going to focus, since it's ready to go, focus on the one that we had some of the most success with in the early days, which was, we call it laser VMX, vitreous multi-material transformation, but essentially it's a laser directed energy deposition process. So think of it like an SLS process in additive manufacturing, but more at a construction human level scale. And so some of these are early TRL3 results, just brand new, our first DOE there with the stripes. You can see feed and speeds change the surface tension, which changed the melt dynamics, which was just really interesting stuff. But still at TRL3, we started in atmosphere with our process and our laser hardware, both located in atmosphere, in a very safe shipping container with dust ventilation and all of that. But then we moved over to having just our process in vacuum, because the properties are going to change substantially, but we didn't have a laser system that was vacuum compatible. So we started working towards that, ended up with both the process and the laser hardware as a subsystem, both in vacuum. So as any good TRL3, I wanted to share with you that we had some opportunities for learning, things like melting our lasers and exploding laser sight glass, and just all the fun that you get to do when you upfit hardware for vacuum environments and challenging thermal environments and all that. But in the end, I feel like we were successful in a TRL3 test. And moving on to TRL4, I call this component and process validation. So we're taking these processes that we've matured in their subsystem levels and putting them into a more complete, cohesive system that would be capable of doing a full end-to-end demonstration CONOPS on the lunar surface. Sorry, let me go back. So what you're seeing there is, this is just a robot manipulator with a scoop. We're doing filtering. We've got lasers adjacent to cameras. We're able to scoop, tamp, filter, build up in the X, Y, and Z directions using molten regolith. So then TRL4, we start doing a lot more component and process validation by way of modeling. So we're doing laboratory testing, but also doing DEM and thermal FEA type models or thermodynamic models to understand what the melt pool dynamics are. Then we're testing in the lab. Sometimes we test in the lab and we learn learn about what happened after we get the modeling results. But that's more of a TRL4 type activity. And then we start exploring, in atmosphere while we're doing the process level testing in vacuum. We start looking at ways to scale. We start looking at optimizations. The one in the middle is actually the center of this kind of landing pad representative element, we call it, and we've employed some topology optimization to actually encapsulate raw regolith within the melt structure, just to lower our embodied energy per unit structural performance. And I call this TRL 5.6 because this isn't the right venue to argue the TRL 5.6 nuance, but essentially we need to take this prototype system that we have working in atmosphere, producing these representative elements, and moving them to where the entire integrated process is now in vacuum with the robot arm, the tool head, the manipulator, all those different things, so that we can really feel the system as a whole. So there's the kind of the hero shot of it operating in our TVAC chamber out of Austin, Texas. And this is what we hope for in the future. TRL 6, this is our fingers crossed TRL 7 moment rather, where we hope to do a lunar demonstration mission. And so we're laying the groundwork to kind of close out the last tasks of TRL 6, things like more robust robotics, things like flight viable or flight designed power levels and associated electronic umbilicals and thermal management techniques. And then we hope to, once we've demonstrated, we can close those lab results to further inform the sort of TRL 8-9 type systems where we start looking at building human scale construction at scale with lunar night survivability and all the other things that these wonderful folks here at this conference are working on. So essentially that's our roadmap of our TRL maturation, and hopefully we're ready to go by the end of this year.
Well, great, thank you.
Evan, I'll bet you if we had a debate on 5 or 6, this crowd would love it. I'll bet you. I know I would. Get back into the technical stuff. Anyway, thank you. It's great to be here. For those who were here for the panel before lunch that I was on, and those online that were watching, you may see some of the, a couple of slides that are the same, but in the interest of those who maybe just joined, I'm going to go through those, so I apologize for the duplication. I do want to also restate what I did this morning is thank you to LSIC for hosting this, and thanks to all of the people here at APL that put this together and do all the hard work to put these together twice a year, because I know it's just an incredible lift, so thank you. So on the ready to go from Astrobotic, just a little bit about our vision, because it aligns with what I'm going to show you here, is we really want to make space accessible to the world, really through space transportation, mobility, and power services, which will be the key to this part of the presentation, for customers around the world. So I'm going to talk about landers, which are ready to go, and it's going to be a little bit of an overlap of the getting gear on the surface talk earlier, rovers, and lunar surface power. And believe it or not, all three are interrelated to lunar surface power. So, lunar delivery. We've got Griffin Mission 1, which is targeted to launch at the end of this year. It's a 650 kilogram class lander, what I call a medium class lander. Be the largest CLPS lander to go to date. This is important because we do need different size capability for really the world and to build this lunar economy. The smaller scale ones, certainly we still need to have for science instruments and so forth, but to start building the lunar surface infrastructure, we need the larger landers and that capability to come online. So, for Griffin Mission 1, again, those of you who saw this earlier, but I don't have any problem showing this again, and I'm sure my Astrolab customers don't mind it either. We're taking the Flip rover to the South Pole at the end of this year on the Griffin lander. This capability is just about there. We're finishing our phase 1 AI&T work. Our suppliers are getting close to delivering propellant tanks, engines, and so forth. All of our flight avionics boxes are done. We do all that in-house, and they've all have passed qualification and ready to go. And here's the deployment of Flip rover onto the surface. As you can see, it comes down ramps that part of which were originally designed for the Viper rover. We were able to reuse a lot of that design to enable Flip to go onto the lunar surface. And they'll be able to test out their technologies for future use on their future rovers as well. So we're really excited about the partnership that we have to take Flip to the lunar surface at the end of the year. So with that, Griffin will be a certified medium-class lander at the end of the year. A lot of the systems that we have on board already flew on our first mission, Peregrine, 18 months ago, a lot of which have reached TRL 8 in a lot of cases, and sometimes 9. All of the subsystems, major subsystems were tested out and worked very well, so we have incorporated those onto Griffin. Moving on to rovers and surface tech. So Astrobotic has a rich history in mobility design and development through rovers. A lot of that came from Carnegie Mellon University, where this kind of Astrobotic was born out of. And we have several different size rovers that we've built, from 2U all the way up to 16U. And then I'll show you a prototype one later that's much larger than that. You can see in the top left, that is our Lunar Grid Light engineering model rover. Lunar Grid Light is a lunar power surface that we intend to take to the moon and test out. That is near ready to go. In fact, we'll be holding our critical design review here coming up next month. And thanks to NASA Tipping Point Awards to help build the backbone of lunar surface power. And then we've got our Cube rover Mission 1 rover in the top right. Again, I talked a little bit about this at the panel before. This is a rover we developed in-house that's flying on the Griffin mission at the end of the year. We have a joint mission with Mission Control, who developed the Spacefarer software platform that will be tested out on Cube Mission 1. So we're pretty excited about that. That picture in the lower right is up in Ottawa in their lunar surface testbed area. We sent commands from Pittsburgh, where Astrobotic is headquartered, and we were able to command the rover while it was in Canada. And then when the engineering model came back to Pittsburgh, Mission Control was able to do the same, command it from their Mission Control operations center and drive it in our lunar testbed in Pittsburgh. So it's a great joint mission, and we're excited about that. Moving to lunar surface power. So I'm sure you're all very familiar with the Moon to Mars strategy and objectives. And if you look in the lunar infrastructure section, you'll see at the very top that that is a priority, is to develop lunar surface power generation and distribution. So what Astrobotic is doing is developing these type of systems that align very well with the top priority in the Moon to Mars objectives. And STMD put out last year the gap analysis. And in the very top two, as you can see, it's power generation, which is a gap. And so Astrobotic feels like we're really a first mover advantage on getting lunar surface power developed and ready to go here in the near future. So our solution to that is what we call LunaGrid, and it'll provide power on the lunar surface in a couple different ways. Let me see if yep. So can I go back? There we go. You'll see in this concept to the right, there's our VSAT technology, our vertical solar array technology, which is actually deployed on a rover. It would be taken to the lunar surface on our lander and then deployed out to whatever distance we want, and then the tower would be deployed up. This is important, certainly in the South Polar region, because you can go very high with a VSAT and have nearly 100% coverage with solar power to be generated at the South Pole if you get it high enough. And we envision several of these type of VSAT towers to be deployed to basically set up a lunar grid network on the surface. You could also keep that VSAT on the static lander as well. So you don't have to go out onto a rover. You could have several landers with a static tower where you could deploy from there. And then I'll talk about the rover with that disc-shaped object on the front here in just a few minutes. So we've actually, again, through Tipping Point Awards through STMD, so again, great partnership with NASA and Astrobotic, to develop the VSAT technology. where you'll see that is a solar array being deployed on a roller mechanism. We took it to the Johnson Space Center last late summer, early fall, took it into the TVAC chamber and actually did some good testing there. Had a little bit of a technical challenge on the deployment mechanism for the solar array tower. We're working with our supplier who provided that to fix that problem, and we hope to get back into the TVAC chamber later this year, actually, to do another test. But we were able to still go down to various temperature ranges and test out the solar array itself. Now, I mentioned when I was talking rovers that I had a much larger rover to show you. So the deployment mechanism that you see, that long white cylindrical part, is the VSAT deployment mechanism. So the solar array is rolled up on that. It is mounted to a prototype rover we call Volt, which would carry that tower and deploy it off a lunar lander. So we also are working to mature that design on the basically the rover system for VSAT as well. And you can see in the lower right probably to scale much better with the person standing next to it. And then I mentioned the Cube rovers for Lunar Grid Light, where we'll actually deploy a rover with a small solar array on it, which will then pay out a cable from the lander with the rover itself. In fact, here's some pictures here of where we have some prototypes on the feed system for the cables, the actual lunar cables. Again, these were all developed under SBIR and Tipping Point awards from STMD. So that dish-shaped object you saw in the concept on the front of the rover is this. It's a wireless charger that we have developed. And we're very, very excited about this. We have wireless chargers that can provide from 100 watts up to 400 watts. And we've actually qualified the 100-watt version of this. We've put it through environmental tests. We've even gone to the point in our lunar test bed where we have basically coated the wireless charger with simulated regolith, and we were able to still get full recharge capability with a component on the other side of it. So the advantage of this is that you do not have to have physical connections on the lunar surface, which would be difficult, right? You can just drive the rover up to an asset that you want to recharge. You don't have to touch, and you could actually recharge through our wireless charger. Or if you had a rover and you wanted to drive up to our wireless charger where it's at, either on the lander or one of our small rovers, you could recharge. So we think this is really a great solution to be able to have this capability to start building the lunar surface power infrastructure on the moon. One other thing we've developed is called spacerless MLI. We all are trying to reach that, right, to get that holy grail of survive the night. And so this was one concept that we've continued to work on, where I can't go into all the design details on it. Number one, I'm not the expert. And number two, there's still some patent pending kind of things going. But what it does is it's an enclosure, as you can see. It's basically a box that has this spacerless MLI around it, and you can enclose your critical systems that you would want to keep warm during a lunar night, and so that you can preserve power and then come out of it at the end of the lunar night and continue your mission. So with that, we're very excited about the lunar power surface infrastructure development work we've been doing in close partnership with NASA. We're looking forward to flying Lunar Grid Light on a third mission of our landers, which would be another Griffin mission, to prove that technology out, and then continue on into the larger infrastructure development with VSAT and so forth. My contact info is in that QR code if you'd like to reach out to me after this, and I look forward to the questions. Thank you.
Great. Let's give, thank you. So we have a few minutes for some questions here. I'm going to start with a couple of questions that are very similar to what Nikki Werkheiser asked her panel yesterday to kind of bookend some of the similarities and comparisons between hardware that's flown and technologies you're getting ready to fly. And then we have a number of questions on Slido as well that we'll get to. So a key aspect that all of your technologies have in common is that they are core foundational infrastructure capabilities that are needed to achieve NASA's Moon and Mars objectives, as well as support an upcoming commercial lunar ecosystem. Given this, what comes next for you in terms of your ideal infusion points, and how do you envision the partnership with NASA continuing? And that's for all the panel members.
Well, I'll start. Well, number one, I'm going to put in a plug here to everybody here would love to take your stuff to the surface. So, you know, think about us. I know, Blue, you've got your own capability coming online, but, you know, maybe we can complement each other. We're infusion points. I want to see us take some of this, what I'll call prototype hardware, and go test it out on the moon, right? Certainly oxygen generation on the moon using regolith, my gosh, I mean, that's core, we need to do that. So let's start taking some of these demonstration payloads to the lunar surface and actually prove it out and learn about that. So how do we do that? We need to have more missions on the books to go take the hardware up there and do this testing that we need to do. Certainly I know that's a challenge with the current budget environment, and it's a lot of uncertainty right now. But trying to read some of the tea leaves, it looks like, you know, exploration of the moon and Mars are key to the administration. I hope we see that in, you know, final budgets coming out of congressional appropriations. And then there's CLPS 2.0, partnering with NASA on what that would look like. We talked a little bit about it with Adam on the last panel with the other CLPS providers. Is in CLPS 2.0 we could envision multiple missions of various capability classes to take some of this hardware up there to test while still doing science as well. All, you know, more missions on the books for everybody. I think that would just really ignite the lunar economy that we're all starting to feel like it's right on the cusp of opening up.
Yeah, I'd say the Lift 1 concept that NASA has is really the right approach to go with. I mean, with our technology, we designed COPR, did that program specifically thinking of what could you do on a Lift 1 sized mission. And we're of the size where we could go on many of these CLPS landers, and there'd still be additional mass capability on those landers that other industry or government could use that capability to get, you know, a lot more bang for their buck in terms of what we're going to actually demo on the moon. So from our perspective, that's the ideal path forward. That's what we've been designing to. There are alternates you could do because I understand the budget constraints and everything else. So smaller CLPS landers, we could break up some of our system to demo things, but really we feel, we've demoed everything in TRL-6, we've shown the end-to-end system. It makes the most sense for us to demo that now. It's the most cost-effective thing to do on the moon. And there are other, you always learn when you're testing, no matter what, even if things go well. So we know we've identified some other things we could spend some IRAD on or work with NASA on to modify our system, make further improvements on it. But I honestly feel like we're at the point where we're getting the ground truth of how the 1.6G environment specifically affects us, and then the real lunar regolith. No matter what we all did at the edges to optimize things, like that information is really key at this stage for us to move the ball forward.
Yeah, excuse me. I'll sort of double down on that. I think, we are starting to understand kind of the intricacies of testing our system in Earth's gravity. And we have modeling that can inform how our system is going to operate on the lunar surface. But I think what you've seen from these recent CLPS missions is that, the trial and error that happens on the lunar surface is really, really important. So I think there's an opportunity, I think there's kind of a critical mass point of this, where once there's enough infrastructure on the lunar surface, then there can be a more targeted pull toward technologies that solve specific problems. And I think until that happens, it's going to be a lot of these kind of one-off demos. But I think there might also be opportunities for, near-term objectives, whether it's Lift 1 or some other instantiation, to support near-term Artemis goals, where maybe there's some acceptance of risk that we can try to employ some of these technologies, drive them towards specific requirements with the understanding that there will be trial and error there that we can learn from long term.
Yeah, I think specifically for infusion, I think we sort of separate robotic technology and human exploration, or at least I have historically sort of kept those as separate things. But when you add up all of the robotics and process capability that this group has and the other folks that are in this room and online have been thinking about and have been working on, once you integrate those, and you can actually find a value stream that closes, maybe not quite yet for the cislunar economy, but certainly in support of humans exploring the moon or Mars. So we could have robots that are making our power systems, that are building protective structures, or making rocket fuel for our return flights from Mars, for instance. And I think the Lift 1 idea is a wonderful way to sort of build a mission that demonstrates that closed value stream. And actually, then we can start integrating these more mature TRL 8-9 technologies into something like the human landing system, Artemis for the moon, and whatever comes of Mars in the future, so that the robots prepare this environment for when we get there. So I'm very pro-robot before human getting somewhere, because I don't know what kind of price you put on decreased risk for a human mission, but I think it's up there. I think it's something that we really need to be investing in and infusing these earlier techs once they hit maturity into the appropriate mission directorates and architectures.
Great, thank you for those answers. It is often said that a key role of the government is to provide the strategy and stability to do the things that aren't yet profitable for industry and or are common problems that multiple industry stakeholders need to be successful. What type of utilities or interoperable systems could the government provide that would be most beneficial for you to develop these technologies effectively and efficiently? And do you talk about these types of systems as a community?
I think, infrastructure has always been something that the government has taken a lead on. And so there's a lot of systems, I think, that, no matter, like, take oxygen, production, for instance, whether it's MRE, carbothermal, something more like hydrogen reduction, you're going to want to have to, collect that oxygen at some central depot. You're going to need to liquefy it and hold it there. So I can easily envision multiple technologies on the lunar surface that are making oxygen, but it would probably make more sense to have a piping infrastructure and a storage infrastructure, liquefaction infrastructure that is kind of unitary, and that could be something that the government provides. Or, I know Astrobotic has their power distribution center, so I'm not trying to step on your toes, but, power lines, power transmission, because everybody's going to need power there. Or roadways, things like that. That, at least to me, shows that, we're a capitalist society. And when I go to my CEO and advocate to spend IRAD to develop our technology, they want to see their ROI. And administrations change, NASA's direction's going to change. We can't control what's going to happen 4 years, 8 years from now, and we're talking long timeline things. But if NASA's helping with infrastructure build out now, that shows a seriousness and a kind of permanence of making that direction towards the lunar economy, no matter which way it meanders. And that's something that I can really use and our leadership can use to fund internally investments.
I think in this scenario, even if like Astrobotic is providing power itself, there's still a coordination of the usage of that power that has to be coordinated amongst all the players.
Absolutely, and just to pull on what you both just said, from a power standpoint, setting the standards for power. What is it, right? What I'd like to see, and what from an Astrobotic standpoint, and personally, is that I'd like to see the government take the lead on setting the standards for power, and so that we don't have multiple systems up there that might have different power, standards, right? So it's kind of back to U.S. versus Europe on power, how we do it here terrestrially. We don't want to do that. We'd like to have one standard so that you've got that interoperability, right, for all infrastructure, not just U.S. developed, but Europe-based, Japanese-based, whatever it is, from a global community standpoint. If we had one standard for power, anybody could use that wireless charger, right? We could provide power to any assets, not just specific ones that were developed just for that, the U.S. type. So I'm all in favor of setting a standard and NASA taking the lead on that to do just that, is set the standards so that we all kind of lead the way and develop along the same lines. We all go together, right?
Sure.
I think there might be an opportunity for setting kind of initial build out of infrastructure, and kind of to your point about power standards and that sort of thing. You know, if sort of a lunar base were established and that's driven by NASA, then I think that provides opportunities for people to see where they plug in. And so I think maybe some of it is, you know, providing near-term infrastructure with consistent landing sites and what the roadmap is there. And then I think the economy can sort of evolve around that. And commercial players can look at opportunities for expanding that infrastructure in constructive ways that's synergistic with NASA drivers.
Anybody else? All right. Here's a heavily upvoted question. Other than money, what is the #1 barrier to flight for your technology? What testing do you need to do yet? What supporting flight capability, power comm, et cetera, do you need for a successful flight demo?
I can probably take that one first. So the technical challenge, as you saw earlier with that wonderful Firefly video, systems level integration is relatively well understood. So you had multiple private parties talking on common buses. You know, we don't necessarily know the power grid standard for the moon yet, but we certainly have a pretty good understanding of what the communication and power systems on a lunar lander are going to look like, how you interface with them. One of the challenges I've seen, though, is as you look to scale these technologies, things like we have a relatively high power requirement, much less than your average household, so it's not megawatts or anything like that, but these CLPS landers are not made to support a payload like ours. It's not a one-size-fits-all solution. So I know CLPS 2.0 is an evaluation, but sometimes maybe the CLPS mechanism just isn't the most appropriate. And so what's keeping us from being able to just apply and hop on a CLPS, you know, say we need 20 kilograms and 5 watts, that's great for some payloads, and it's just not for an integrated mission. The other parts there, we have to talk and we have to actually share each other's roadmap. And I think the Lift 1 idea of old and hopefully re-emerging sometime soon is encouraging people to partner up and make a end-to-end more cohesive mission, something that can start to at least scratch at closing all these value streams. And so if I have a robot arm, for instance, that wants to shoot a laser at the surface of the moon, and somebody else needs their MRE system loaded by my scoop, by all means, my scoop should load them and then go back to work. And I should be able to take their molten regolith and cast it into bricks to demonstrate making a cobblestone road. So all of those things don't fit necessarily into that 20 kilogram 5 watt box that we can stack 15 of them on. So I think what we're missing really is not necessarily technical in nature. It's partnerships, it's intellectual property agreements, and it's obviously the old interoperability. So
I guess I would add, and you heard me kind of pound this at the last panel, of supply chain. Unless you're completely 100% vertically integrated and you produce all of your own hardware, there's a throughput problem in a lot of the major system supply chains today. And there were a couple of forums that were sponsored by the CLPS office earlier this year on engines, thrusters, propellant tanks, and so forth. And it was apparent that there is a throughput problem of these companies being able to support multiple customers on the schedules that they need hardware delivered. And so I think that's another constraint that needs to be looked at from a supply chain, industrial-based standpoint, is if we're really going to start ramping up the number of missions and we want to get infrastructure there in a timely fashion prior to humans getting there and getting them set, and even during for logistics and so forth, we're going to need to have a much stronger, deeper supply chain to enable all of this.
Great. We are out of time. Let's give our panelists a hand, please. Thank you so much. I did notice there are a lot of questions that came on to Slido, but there is a show and tell this afternoon. There are a lot of questions for you individually. So if you put a question in for one of the individuals, please come to the show and tell today, I think at 4:30, and get your question answered from them there. Before we go to the next panel, I do need everyone's help real quick. We need to shift gears. Help me with some NASA administrative business real quick. I was asked to bring this down and present. We celebrate milestone anniversaries at NASA. There are significant events in our people's career. I was asked to bring 2 service awards down, and so instead of just giving them to them without an audience, I thought we could celebrate them together real quick. So we'll do this very quick if that's okay. To recognize 25 years of service to NASA, this service award goes to Quinyao Nguyen, our incredible. I'll bring it over to you in a second. And every 5 years, you get a new NASA pin, and it gets fancier and fancier. This one, I believe, has a sapphire in it with 25 on it. So I'll bring it over to you in a second, Quinyao. In recognition of 40 years of service, this service award goes to Fred Elliott. Wow. 40 years is when they put the diamond in it. So Fred, I'll bring it over to you in a second. Thank you so much. Okay, we're ready to go. Thank you for that.
Okay.